Hello, my name is SangjunLee and I'll be presenting on a design pattern named Reactor. I would like to start from describing a situation where the Reactor design pattern would be suitable. Let's say we need to build a server for a server client network. The network consists of multiple clients and a single server. So the server needs to be responsive to all the clients simultaneously. Perhaps the most intuitive way to develop a concurrent server is to use multiple threads. This approach accepts multiple network connections by spawning a thread per connection to handle client requests. However, there may be some drawbacks on this approach. First, multi-threading may end up making too much overhead from context switching, synchronization, which will lead to poor performance. For instance, long-living connections like keep-alive connections would result in a large number of worker threads waiting in the idle state. It would cause context switching whenever the server just wants to check if there's any input. And second, threading may require complex concurrency control schemes like deadlock, transaction control, and etc. Portability may be a critical drawback of this approach in case you want to port the system to another OS that does not support threading. The Reactor design pattern gives a simple solution to do what we want while maintaining the simplicity of single threading. This diagram demonstrates the difference between the multi-threading approach and Reactor design pattern. As you can see, there's only one thread handling the multiple clients connection and their requests. This is a class diagram of the Reactor design pattern. The required event handling, or the things the server needs to do when receiving each event, are implemented as event handler. And the reactor is dispatching mechanism of the reactor pattern. In response to an event, it dispatches the corresponding event handler to the synchronous event demultiplexer. One of the most important parts of the design is the synchronous event demultiplexer. It is the part that allows the system to act asynchronously by waiting for the event on the OS side. Synchronous event demultiplexer is based upon existing OS mechanisms rather than developed by implementers. One of the OS mechanisms that support this feature is select system call. The select system call is supported by Unix and Win32 systems. This is an abstract of how the reactor works. First, the reactor passes an event to the synchronous event demultiplexer. Then the synchronous event demultiplexer waits for the events. And when the events come, the multiplexer wakes up and the demultiplexer calls back the appropriate handler. And 4, the event handler performs the actual read operation, handles the data read, declares renewed interest in I/O events, and returns control to the dispatcher. Okay, let's take a look at the example code I wrote in Python. This example is a simple server using socket connection. This server can handle 2 types of requests from multiple clients. The requests it can handle are accept connection and read. The synchronous event multiplexer in this example was implemented using selectors library, which lets the OS to call back when a certain registered event happens. This program consists of 3 parts. The first part is event handler. So the event handler is the parent class, and the 2 concrete event handlers inherits it. Accept event handler defines what the server needs to do when a client requests a connection, and read event handler defines what it should do when a connected client sends something. The second part is the React class. And the third part is synchronous event multiplexer. So when the program starts, it simply initiates the Reactor class, and when the Reactor class initiates, it starts a socket server. And since it's going to use the synchronous event demultiplexer, it generates an instance of that class. Then it registers or dispatches the accept event handler to the synchronous event demultiplexer. It uses this function here. And I'm going to start a test. I'm going to start this server and open a test client. So when the server receives the connection request, it prints this log, and then it also registers the read event handler to the synchronous event demultiplexer. So now the demultiplexer is waiting for two types of events. The first one was accept event handler, which was added here, and now the read event handler was added here. So now both concrete event handlers are in the synchronous event demultiplexer. So it's ready to be responsive to both of them. So first, so here when the client sends anything like hello, then the server will echo hello back to the client. And when you start the second server, since the synchronous event demultiplexer is waiting for the connection request as well, it can receive the connection as well, and it can also send back the message from the second client, like vice versa, like that. So the most important benefits is that the design can build a system that can comply a concurrency using a single thread. Also, since the pattern decouples the codes into separate classes, it enhances the modularity of the program. One of the drawbacks of the pattern is that it's non-preemptive while performing a blocking IO process on the thread. So the thread should avoid handling a long process. The existing softwares that use this pattern are Node.js and ACE framework. The Proactor design pattern is a variant of this Reactor pattern where you can handle events asynchronously using multiple threads. Here are the references for this presentation. And well, thanks for listening.